Recently on my channel, I hosted, maybe I'll clear my throat before I try to start talking. Excuse me. Recently on my channel, I hosted a debate between, or it wasn't a debate, it was more of a discussion between William Lane Craig and Graham Oppy. Both of these guys are experts in their field. They're both philosophers, and they were talking about a particular argument for God's existence from mathematics. It's an argument that Dr. William Lane Craig has used a few times over the course of his career, and it was a fascinating discussion. It was super interesting, but it was a little difficult to understand at points. And so what we're doing today, I've got Dave Hutchings with me. He is a physics teacher out in the UK. He's super smart. He has a knack for being able to break these things down on a level that anyone can understand. He's a teacher, after all. And so this is an explain it like I'm five version of this debate, this discussion that we hosted on our channel. So we may, if this goes well, we may start to do more videos like this where we break things down at a level that anybody can engage with. Because I mean, if you watch that thing, it was difficult to follow at points. Like, I even mentioned, we probably should have had the clip of it, but I even mentioned, I was like, can you guys stop and explain this to me like I'm 5 years old? And then right after I asked that, they just like kind of kept on going. And then, anyway, so that's why we're doing this video, is to help break what they talked about down. And we have so many amazing things planned for this video. It's amazing. Like, Dave went into his lab, he recorded a video. We're going to play that video and how it all works and everything. And then toward the end of the video, I'm actually going to give an analogy that I came up with to explain some of Graham Oppy's views. I ran it by some other people that really know his work really well, and they agreed with it. So a lot of really cool stuff. Well, Dave, it's great to have you back here. I'm really thankful that you put all of this work into this video, that you recorded your video and you've talked to other people about explaining these things. You've even reached out to Dr. Craig himself and ran by some of the things that you have planned to talk about today. So I appreciate all the work that you've done and put into this already.
No, not a problem. Don't oversell it though, Cameron. If you tell people it's going to be amazing, the only way is down, right? So I'll balance it and say it might be okay. We'll see how it goes.
I think it's going to be awesome. All right. Well, where would you like to start with this video? Because we have a bunch of clips lined up. We're actually going to explain, like, we're going to play a clip. We have 6 clips. Yep, 6 clips that we're going to play from the debate, and then we're going to kind of explain some of that afterwards. But I know that we have some initial things that we want to say before we get to any clips. So, Dave, just go ahead and take it away.
Sure. So the first thing I think is that I thought it was a really good conversation, held in the right sort of way, that both of the people speaking, Bill Craig and Graham Oppy, were positive. They listened to each other, and they actually engaged with what the other person was saying and tried to be fair. I thought it was a really great example of how to have that sort of conversation. But the flip side of that is they're both, like you said, super, super smart. And I think if you asked, I think someone did ask Bill, who's the guy that you would least like to get in a battle of minds with? He said Graham Oppy. And I know that other people have said that about Bill Craig too. They're both super smart, and of course what that means is that when they have a conversation with each other, they're going to pull each other up and up and up and up and up. So it's a very high level conversation.
Yeah.
And not only that, but it's also on topics that are quite specialist. So a lot of the things that they said, a lot of the terminology they used was either high level philosophy, or it was high level maths, or it was high level physics. There was a point in the conversation when Graham said, Dr. Oppy said, I don't have enough physics for this bit. That's great humility, but it also shows you the kind of levels that they were hitting, because they're both pretty switched on, and I think they were stretching each other. It's a bit like watching 2 top heavyweights pull the best out of each other, and we might talk about that again later as an analogy, I think. And then the other thing to say is that the topic that they chose because they felt they hadn't had a proper conversation on that topic before. So I think you got a bit of an exclusive, but I also think that what that meant was they were both working out what they thought about it while the conversation was happening. And that I think that there were times when each one raised an idea that the other one hadn't thought of, and they had to do some thinking on their feet. Whereas I think normally those discussions would happen through academic papers, and you get the chance to read and digest the paper. And so it makes it even more impressive that they were responding in real time to some very, very clever points that were being made by the other. And then lastly, they chose a particular paper from 1959 by Eugene Wigner, and I've got it here. I highlighted key sections, and then my daughters scribbled all over it after that. So we'll see what we can come up with from that as well. But that paper is in the public domain, and actually is surprisingly readable. It's called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And it's a very important paper and quite a watershed paper. I think you've got a slide, Cameron, of Eugene Wigner.
Yep.
And of the opening of the paper. Okay, so there it is: the unreasonable effectiveness of mathematics in the natural sciences. And this paper, the key point from this paper, really, there are several, but the kind of general gist of it is: look, there's this thing that human beings do called maths, or in the UK we call it maths, and you guys call it math. There's this activity that human beings get involved in called maths, and it kind of sits over here, and it's in some senses it's its own world. It's a complete self-contained world where mathematicians kind of get stuck into it, and they solve all these problems and they play around with all these ideas. And then you have this other world, physics, which is saying, okay, let's describe the universe we're actually in and find things out about it. And there's this just really weird, unusual, strange connection between the two, that these ideas that the mathematicians are playing around with in this world, this kind of other sort of world, abstract world almost, those ideas turn out to be very, very useful in this world, the world where we're actually doing physics and we're studying the way that real objects behave in the real world. And he asked the question, why should that be? Why should this world have anything to do with this world? And actually, in his paper, he doesn't give a final answer. I think is there a follow-up slide where he kind of ends up? Yeah, here we go. So I actually, from my screen, I'm not able to read all of that, Cameron. I'm guessing you are. So do you want to read that out to everyone?
Yep. It says the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift which we neither understand nor deserve.
So that is the conclusion of his paper. It's interesting that the word miracle is in there, and actually the word miracle turns up 12 times in the paper. And he also calls it an article of faith. He says it's an article of faith that you can use maths to do science. So his conclusion isn't really a conclusion, in that it isn't an explanation. What it actually is it leaves the question hanging. It says, look, there's just this situation where maths is really useful, but we don't know why it's useful. It seems almost miraculous that why should these two worlds have anything to do with each other? So what I want to do is try and give you an example of this. Okay, to give an example, I've got a whiteboard here. I've got some whiteboard markers. And for all of those people who kind of think, oh, I hated maths at school and I hated physics at school, sorry, we're going to do some. But Cameron, you're going to play the part of the student. You're going to say, sorry, sir, I don't understand, or can you explain that bit again? Keep half an eye on the live chat, and if people are like, don't understand, then chip in, okay? But I'm going to try and give an example of something that we can do in the world of maths, all self-contained in the world of maths, and then show that actually, surprisingly, it turns out to be useful in the real world as well. And this is going to take probably 20 minutes to half an hour, and I am going to be drawing things on the whiteboard that are going to look mathsy and they are going to look physicsy. Okay, so that's the kind of disclaimer that I've got in at the start, and we're going to start off by doing some maths. Have you got an inspirational "let's do some maths" slide, Cameron?
I do actually.
To get everybody kind of fired up and in a good mood.
Let me see if I can actually make it work. There it is. Let's
start
with some maths.
Okay.
Which, by the way,
now everybody's...
yeah, it's pronounced differently in the U.S. Just letting you know that.
Yeah, I put a stripe through the S, just to help you guys out a bit in case you were already confused.
Thank you.
So I'm going to start off by doing some maths. So this is all going to be sitting entirely in the world of maths, right? So we're going to start off by drawing a circle. Okay, a nice simple shape. A circle is one of the most obvious shapes that you could draw.
Wait, I don't understand.
So we've got this circle drawn, and we're in the world of mathematicians. Okay, so the mathematicians are not asking real world questions. They're asking questions about just maths. They're just doing it for fun. They're just doing it out of curiosity. They're coming up with ideas. They do not have to be connected to the real world at all. They're just enjoying themselves, these mathematicians, okay? Now, the reason they do this sort of thing is that they probably don't have any friends, but they're finding other ways of entertaining themselves. So we've got a circle. We've drawn a circle. And what I'm going to do, I'm going to draw a line through the middle of it that just kind of goes along across the board like this. And a question that we could ask about this circle is, all right, well, what can I do with it? What things can I study about this circle that might be interesting? And one of the things I can do with a circle is that I can just go round it, right? I can keep going round and round and round in a circle. It repeats itself, okay? So this is already quite a lot of fun. I'm going around a circle. And then one of the questions that might arise is I could say, okay, well, let's stick an arrow on the end of this here, okay? And we're going to say, all right, well, what's our experience then? If we're going to go round and round a circle like this, what's that going to look like? Okay, well, here's my starting point. And I'm going to start at this point on my circle, and I'm going to go around like this. Now, if there are any mathematicians watching, they're not going to like that very much, because did you know this, Cameron? When a mathematician goes round a circle, they start here and they go the other way around. Okay? And so they would be very upset at the idea that I might start. Yeah. I'm going to start here and I'm going to go this way around. If you are a mathematician and you're upset by that, just imagine being on the other side of the board. Okay? And then you'll be happy. So what we're going to do is we're going to think, okay, well, as I go around this circle, what happens? And the first thing is that I kind of go up until I reach the top. Okay? So if I draw that, I'm going to go up the circle until I reach the top. And then when I've done that, I'm going to come back down again gradually and then fast. And now I've got back down to the bottom again. Okay, so with me so far, Cameron?
Yep.
I might extend that line out a little bit. You can see that I'm not an artist. Okay, just try to make it look a little bit like it's the same. Now, once I've got here, I'm not going up anymore. I'm now going down. I'm going down quite steeply at first until I reach the bottom of the circle. So I'm going to go down and I reach the bottom of the circle. And then the last thing that I do is I start going back up and I get back to where I came from. And so it kind of looks like this. I might extend my arrow out a little bit further. There we go. And so as I go round the circle like this, I first go up, level off, then I come down and level off, and then I get back to where I started from. And so my circle, the process of going around my circle, can look like a wave. Is that all okay?
Yep.
Yeah. I think you've got a little graphic, a nice little animated graphic, which I call a GIF. Some people call it a GIF, but I think it is a GIF. And you can have a comments war about that later if you want. So. All
right, so let me go ahead and put it up on the screen here.
Yeah, you go for it.
Beautiful.
Okay, so there you go. You know this was put together by a mathematician. Cameron, how do you know that this particular one was put together by a mathematician?
Because it's going the right way. You have it backwards on yours.
Yeah, that's right. Okay, so it starts in the right place. Oh, I see. You've flipped it on mine, have you? Okay, right. So you can see this wave is clearly something to do with the circle, right? So you can turn that back, and we'll do the next part of our journey. Okay. So clearly, this wave has got something to do with this circle, right? They're clearly related. The information in this wave came from this circle. That's where it came from. Now, what a mathematician wants to do next then is say, okay, can I figure out anything about this wave? If I study this wave, is there anything interesting that I can see about it? And there are lots of different questions they could ask about it. But here's one question they could ask. They could ask the following question. They could say, right, I'm quite interested in how steep this wave is. So it's very steep at the start, then it gets less steep, then it goes flat. Then it gets steeper, then it gets really steep, and then it comes down here and it starts to get less steep and so on. So they might say, right, I'm interested in the steepness of this graph. So of this wave. So I'm going to call this one steepness, right? I mean, you can tell these are fun guys, right? These mathematicians, they're fun guys. So we can say, right, when it's very steep and it's going up, right? So that's steep going up. Down here would be steep but going down, and then if it's flat, we'll put it in the middle. Is that okay?
Yep.
So what's it doing at the start here? How steep is it at the start?
Very, very steep.
Yeah, and is it going up or is it going down?
It's going up.
Okay, so steep up, we'll put a point there, right?
Okay.
And then let's say, okay, well, this looks like a next important point. So what's it doing there? Is it at the top here? What's it doing? How steep is it?
It's flat.
It's flat. Okay, so we can put a point here for flat. And then let's say, well, what about this bit here? How steep is it here, Cameron?
It's very steep.
Yeah, and is it going up or down?
It is going down.
Okay, so we can put a point there for kind of steep down. And you can maybe see that this is now going to repeat itself, but the other way around. So it's flat here, and then here it's steep, and it's going up again. So what I could do is I can join these points together. And what I've produced here, like this, is a new line. And what this line is telling me is how steep my first line is, right? This line is telling me how steep my first line is, and I can double check that. I can check any point. So if I pick a point like, say, this one here, I can say, right, well, what's it telling me? It's telling me it's kind of halfway steep, and it's going up. So let's just check that. Is it halfway steep going up? Yeah, it is. Look at that. That's amazing, right? It's kind of half steep, and it's going up. What if I pick, say, this point here? This point here is telling me it should be going down, and it should be pretty steep. Let's just check. Is it going down, and is it pretty steep? Yeah, that works as well, right? Or I could pick a point here, and I say, all right, this is telling me it's quite close to being flat. It should be going down still, but quite close to being flat. So let's just have a look. Yeah, there it is. It's going down, and it's quite close to being flat. So have I convinced you that this line is telling me how steep that line is?
Yep.
Okay. Well, I mean, mathematicians, they're a persistent bunch. So now they've got a new line. What do you think they want to do with this new line?
Are they going to... I don't know.
Yeah, they're going to study it again, right? You're right. They're going to study it again.
Yeah. Okay. Go ahead.
Go on. Were you going to say something else?
It seems to me like the only other thing that you could do, because you kind of did halfway. So, I mean, you'd probably start going down this next time.
Okay, well, let's see what happens, shall we? What they decide, one of the things they could decide to do, these mathematicians, is they could have a new line, and they could call this one the steepness of the steepness. Yeah, you don't like that word, huh? Or
don't like what?
That word steepness. Are you happy with that? The steepness of the steep. So this is now going to tell me, I'm going to draw a line here that's going to tell me how steep that line is. Well, we'll do it a bit quicker this time because we get the idea, I hope.
Yes.
So here it's flat. So I'll put my cross there. Here, it's very steep and it's going down. So I'll put it there. Here, it's flat again. Here, it's very steep and it's going up. And then here, it's flat again. So now I can join these lines together like this, these points together. Okay. And I've got a new line, and this line is the steepness of the circle, right? The steepness of our circle line. Okay? Now,
I have some bad news.
Yeah, go on.
We got a downvote on the video.
Oh, well.
Yeah, some
only
people
one,
just...
Right? Only one.
Yeah, only one. 67 likes. Which, by the way, if you were liking this video, hit the thumbs up button and subscribe. That's a good thing you can do too.
Yeah, do that. Yeah.
Yeah, this is fun. You've got to start to tell me where this is going though.
Yeah. Oh, I know. Yeah. Well, don't worry. We're done. We're nearly done with the math, right? So.
Okay.
What we have discovered here. I mean, we're looking at these. I want to check how observant you are. Do you notice anything, Cameron, about this line and this line?
Yeah, they're the opposite. They're mirrored.
They're the opposite. Okay.
Across the x-axis, to use a Michael Scott quote.
Yeah, this one's the opposite of that one, and so actually, mathematicians are pretty pleased about that. What they can do is they can say, right, let's give this a name, give this line a name, and they called it sine, right, S-I-N-E. And it turns out that if you take the steepness of the sine line twice, then you get minus sine. So if I take the steepness twice, I'll do two arrows. So the first one's the first steepness, the second arrow is the second steepness. I get minus sine, right? Now, I'm not a mathematician, okay? And so I find that mildly interesting, perhaps, but it doesn't float my boat. And of course, one of the reasons it doesn't float my boat is that I'm not thinking about floating and I'm not thinking about boats. All of this has happened entirely in the abstract world of mathematics, okay? We haven't talked about the real world at all. All we've done is some maths. We started with a circle, and then we got these lines here, right? Happy?
Happy.
Okay. Can you fill for like 2 minutes or a minute while I just wipe the board?
Sure. I hope you guys are enjoying this video so far. As I mentioned, we have a lot of cool things planned. We're going to have these clips. We have these clips queued up, and we also have a video that he's going to play in probably, 10, 15 minutes about the where you went into your lab, which is actually really, really cool. Yeah. So I'm really excited to play that one. But the very last section where we get to Oppy's explanation, I'm really looking forward to that one too. We're going to kind of switch roles, and I'm going to do what I can to explain that one.
That's right. You're going to try and get us some upvotes to cancel out the downvotes. How are we doing on downvotes now? A few more?
We're at 2 now. Yeah, we had 3, but now we're at 2. I think people were just.
Can the same person downvote twice?
No, they cannot unless they have multiple accounts.
Okay. Right, let's do some real world stuff then. Let's do some actual physics. So here, this thing here, let me just get the rest of it in my hand.
Okay.
This is a pendulum, okay? And by a pendulum, I basically just a mass on a piece of string. And when I move it like this, it swings backwards and forwards, okay? Now, this is clearly a real world thing now, okay? We're now in the real world. This is something that's actually happening in the real world. And it turns out to be a very useful thing to study. And the reason it turns out to be a useful thing to study is the way it behaves. Basically, it has a position that it would like to be in the middle. That's where it would be if you just left it alone. And if you do something to move it away from the place where it would like to be, it tries to get back. But when it tries to get back, it overshoots it. It goes past it, and it has to come back again, right? So there are lots of things that behave like this. Here's a pendulum. It's not the only thing that behaves like this. So a guitar string would behave like this, right? It has a place where it wants to be, just sitting down on the guitar normally, and then you pluck it, and then it tries to go back, and that means it goes backwards and forwards and backwards and forwards. And also, this is how lots of molecules behave, right? So like the oxygen in the room around you right now is also behaving like that. as soon as it gets bashed, it kind of wobbles back down to get back to its normal state. Okay, so studying these systems that do this, that try to get back to their middle point, is really, really helpful in physics, and so that's one of the things we do. So what we're going to try and do is we're going to see if we can figure out a couple of things about this pendulum, right? And the first thing we're going to do is we're going to try and draw a line that tells us where this thing is as time goes on. Okay, so I want to start it off swinging, and then we're going to draw a line that tells us where I'll be able to find that pendulum bob. Okay, so here we go like this. Well, I'll try and be quick. It starts off in the middle. Okay, we're gonna start our timer in the middle. Okay, I'll start our video in the middle or whatever. And then what I really want to do, really, to keep this simple, is to go off to the right next. But is that your right, Cameron?
That's my right, yeah.
That's your right, okay. So it's going to go off to the right first. Okay, so it goes up to the right. Then where does it go next, Cameron?
It goes back to the middle.
Good, it goes back to the middle. Then where does it go?
All the way to the left.
Good, all the way to the left. Like this. And then where does it go?
Back to the middle.
Good. I can hear the joy in your voice. Now, does that look familiar to you, Cameron?
Yes, it looks like a sine wave.
Yeah, it looks like a sine wave, okay? Well, guess what we could do if we wanted to?
We could flip it.
We could flip it, yeah. Well, we're going to ask a slightly different question. So this is if we want to know the position of where the pendulum is. But what if I don't want to know the position of the pendulum? Okay. What if what I actually want to know is how fast it's going? Right?
Yeah.
So what I'm actually interested in now is how fast it's going. So remember, our starting point was when it's in the middle and it's moving to the right. Okay. So that's it swinging like that, and it's about to go there.
Yeah.
Now, I'm going to draw a line then to show how fast my pendulum is going. And if it's going fast to the right, I'm going to put it up here. If it's going fast to the left, I'm going to put it down here. And if it is zero, if it's stopped, then I'm going to put it along the middle. Okay? So, Cameron, the pendulum is in the middle and it's heading towards the right. Okay?
Yep.
So you watch it here. Now, how fast is it going?
The fastest.
The fastest. Yeah, brilliant. Okay,
in the middle.
So it's going fast and to the right. There.
Mm-hmm.
Yeah.
Mm-hmm.
Now it gets out to the far right. Okay, it gets out to the far right. How fast is it going when it's out to the far right?
It stops.
It stops. Okay, and then it goes back to the middle where it's going really fast, but it's going fast the other way. Then it goes back to the far left where it's now not moving anymore, and so on. And so I get another line like this. Does that look familiar?
Yep.
Okay.
Yeah, it's,
and then what I could do...
You were doing the same thing with physics.
Yeah, we're doing the same thing. And then finally, what I could do is I could do the whole process again. And of course, we know now that what we're going to get is the opposite of this wave. So it's going to go down first, then it's going to go up like that. But the amazing thing is, this first one was telling us about the position of it. The second one was telling us about the velocity or the speed of it. And then the third one, this line, which we know is the -1 of that, it turns out that this line tells us the acceleration of it. Okay, that tells us how much it's accelerating.
Interesting.
Can you see that bottom line, or is it a bit faint?
Oh, I can see it. It's fine.
Okay, that's fine.
It is a little bit difficult to see, but I think people get the picture.
Okay. So what the physicist discovers when they play around with this stuff is that position, which was our first line, is the opposite of the acceleration, right? I'll put an equals there, and a lot of people will get grumpy about that. But it would be true if you pick the right constants. So position is equal to the negative of the acceleration. And what that means, Cameron, is if I know where this thing is, I also automatically know how fast it's accelerating. Okay? So clearly, there is something that pendulums, which are real-world systems, have got to do with circles. They must be related somehow. There must be some hidden relationship between circles, because when we got these lines before when we were doing math, we just got it from a circle. And when we're doing the lines now, we're getting them from like the position and momentum and acceleration of a pendulum. So why are they related? What have they got to do with each other? And at this point, I think you've got a video that you can show people, and they can have a bit of a break.
Is this the one? Is this the one of your lab?
Yes. Yeah. Go for it.
Perfect. All right, I'll go ahead and play it now.
Welcome to the lab. This is where I do my day job. And, oh, wow, those look like some really, really good books there. Anyway, let's crack on. What have circles got to do with pendulums? Well, here is a turntable, and I'll give that a spin like that. And you can see that there's some plasticine on there, and the plasticine is going round and round and round in a circle. It's got a thermometer stuck in the top of it. And you'll notice if I just turn the lights down, and then I turn this light on, we can have a look at the shadow that it's making. And now that looks familiar. In fact, if we go around this side and have a good look at it kind of front on like this, the shadow just kind of looks like a pendulum. So the question is, does that require some kind of explanation?
Okay, so it turns out that there is some deep relationship between the maths of a circle and the physics of a pendulum, right? And in this paper, The Unreasonable Effectiveness of Mathematics for the Natural Sciences, Wigner says it's not just in isolated cases. It's not just when you have a circle and a pendulum. There are all sorts of other situations as well where an idea that first shows up in maths and that people were just playing around with turned out to describe something that appeared in the real world. And it happens so many times that the language he uses is, it is difficult to deny that a miracle confronts us here. The stuff that the mathematicians are working on in their own world is showing up in the physics world all the time. And why does that happen? What's key about that? And this is what Dr. Craig has written a paper about, and what he's formulated a new argument. So I think you've got a slide with Dr. Craig's argument from the debate.
Yep, let me go ahead and pull it up here. Have we already done the physics part and you forgot about that slide?
Yeah, I'm really sorry about that.
Oh my goodness. All right, here it is. Got it up here. Yeah, so they can see the whole thing, but you may not be able to.
Yeah, are you okay to read that out?
Yeah, I'll go ahead and do it. Dr. Craig's argument, premise 1, mathematical concepts arise from the aesthetic impulse in humans and have no causal connection to the physical world. 2, it would be surprising to find that what arises from the aesthetic impulse in humans and has no causal connection to the physical world should be so significantly effective in physics. 3, the laws of nature can be formulated as mathematical descriptions, which are often significantly effective in physics. And so 4, therefore, it is surprising that the laws of nature can be formulated as mathematical descriptions that are often significantly effective in physics.
Yeah, okay. So if you keep that slide up, Cameron, we'll just talk about it and try and make sure that everyone can understand what Dr. Craig is actually saying here. So the first premise is saying two things about maths, right, and the ideas in maths. The first thing is that they arise from what he calls the aesthetic impulse. And by the way, this is not his own terminology. He has used Wigner's terminology. It's Wigner who says that the maths arise from the aesthetic impulse. This wasn't Dr. Craig's invention or his twist on it. He has actually used that himself. What Wigner says in the paper is the concepts are defined with a view of permitting ingenious logical operations which appeal to our aesthetic sense, both as operations. So this idea that maths comes out of the aesthetic impulse, and we'll talk more about that in a minute. And then the second thing that he says is they don't have any causal connection. Maths can't make anything happen, right? So the fact that we could discover that stuff about the circle and turn it into those lines doesn't make the pendulum do anything, right? There's no causal connection. Maths can't make anything happen in the universe. It's kind of its own world, right? It's disconnected causally from the world. And then the second premise simply says it would be surprising if maths, which can't cause anything and comes from kind of human inventive instinct, actually turned out to be practically useful in the world of physics, right? Or anything like the degree that it does. The third premise says the laws of nature can be written down using maths. And then the last one says, therefore, it is very surprising that the laws of nature can be written down using maths. When you think about the fact that maths only comes from the aesthetic impulse and it doesn't have any causal relationship. And those are the only four premises that he gave in that particular conversation. In the paper, there are three more, but we will come on to those later. Of course, it's quite wordy, and that's because it's written for a philosophical paper. So what I've done is I've rewritten the argument in a kind of explain it like I'm five form. And I have been in touch with Dr. Craig to check that he's happy with it. And with my rewrite, he has given it the thumbs up and said that he's happy for me to use it. In fact, he called it amazing, which was encouraging. So, do you want to read that one out, Cameron?
Yep. Yeah, I've got it pulled up on the screen. Number one, maths is sort of its own little world, which includes lots of crazy or impossible ideas that were invented by human beings for the fun of it. Number two, it would be surprising if these invented ideas turned out to match the real world. Three, they do match the real world. Four, which is surprising.
Okay, now one possible complaint about this might be, hang on, it says own little world, and actually the world of maths is infinite, right? There are all sorts of infinities turning up in maths all over the place. So someone could say it's not a little world at all, but I used the phrase own little world to kind of try and talk about the isolation of it, that maths is its own world, it's its own sandbox, you play in it, and a lot of the ideas that mathematicians have come up with are crazy. They are impossible, they're strange, they're unusual, and we will talk about that as the conversation goes on. And a lot of the time, they're just doing it for fun. They're not actually trying to talk about anything that matters at all. They're just doing it for their own entertainment. And then later, it turns out that those ideas do match the real world, which is pretty surprising. Okay, so that's the thrust of the argument. And then the next step to it, of course, is to say, well, if it's surprising, it needs an explanation. And then Dr. Craig says, okay, the theist has got the upper hand in explaining it over the naturalist. Okay, the theist has got the upper hand. He's not arguing that this is a proof for God at all. And in the same way, Oppy was not arguing that it was a proof for naturalism if you could use the first, you're saying this is surprising, but I've come up with an explanation for it that's naturalistic. So neither of them are claiming to either prove theism or prove naturalism. What they're doing, or what Dr. Craig is doing, is saying this is easier to explain on theism than it is to explain on naturalism. And we'll get to that kind of at the end, really, because that's where the whole thing culminates. But in the meantime, I think we need to look at some of the things that they actually then said to each other. Okay, so I think you've got a few clips lined up. Is that okay?
Yep.
The first one.
First one is that it's
so-
not
so-
an. Oh, go ahead. You set it up.
Yeah, so Dr. Craig has now given his argument, and they're now discussing it. So the argument that we just put up on the screen has already been given, and now it's over to Dr. Oppy to comment on it. Okay?
So we'll go ahead and play it, and then we'll provide comments afterwards. Here we go.
That's right. Yeah.
So the first premise was something like that mathematical concepts, at least certain advanced mathematical concepts, come from aesthetic impulse. And the idea was that the complex numbers, one of the ideas was that the complex numbers is an illustration of this. I think that that's probably not right. So I remember studying some complex analysis when I was doing my maths degree. And one of the interesting things about the complex numbers is what you can do with them. So you can start with real valued equations that you can't solve analytically using real analytic techniques. But by making a transformation into the complex plane, you can do some complex analysis, and then by purely analytic techniques, outpop some real numbered answers. So that the utility of the complex numbers, at least initially, and the reason why mathematicians were interested in them wasn't aesthetic. It was because there were practical problems that they wanted to solve. They wanted to be able to give exact solutions to these real numbered equations. And it turns out that the only way that you can do that is by taking a detour through complex analysis. I think more generally that Wigner underestimates the extent to which mathematics is about problem solving and overestimates the stuff about aesthetic impulse. I think that typically mathematicians are interested in puzzles, especially long-standing puzzles, but puzzles that they want to solve. And then they're looking around for ways to make advances. And when a long-standing puzzle does get solved, the expectation is that lots of new mathematics will follow on its train. You'll remember when Wiles proved Fermat's last theorem some time back, there was some expressions of disquiet amongst some in the mathematical community because they couldn't see that there was lots of new mathematics that was going to be coming out of it. Right. But the general point, I think, is that Wigner is kind of talking up the wrong thing when he's talking about the reliance on aesthetic considerations, because I think that mathematics is much more about problem solving. Anyway, that's a first thought that you might like to say something about.
I think that it's certainly true that these mathematical concepts do find very practical applications. For example, in something as simple as electrical engineering, complex numbers turn out to be critical and very useful. But I don't think it's true that what drives the working mathematician is scientific utility.
Okay, so obviously because Dr. Craig has set up an argument with premises in it, the obvious thing for Dr. Oppy to do is to start looking at the premises and saying, okay, is there anything there that I want to challenge? So he starts with premise one, and premise one was when Dr. Craig said that one of the things about maths is that it arises from the aesthetic impulse in human beings, or that they're doing it for the fun of it in my version. And Dr. Oppy pushes back and says, I don't think that's really the case. I don't think you can say it arises from the aesthetic impulse. I think it comes more from the desire to solve problems. I think there was a slip of the tongue from him. He said it's a desire to solve practical problems, but I don't think he was meaning, that people are only ever trying to solve physics problems. I think what he meant was what they're interested in is solving problems, yes, for the sake of solving some of those problems themselves. Even if they don't have any practical utility, that the drive is to solve problems and to find the true answer to something. And that's not aesthetic, that's a different part of the human psyche. It's the kind of truth-seeking part of the human psyche. And so he's trying to take down one of the premises. And actually, I feel like this is an example, again, I'll use the analogy of a heavyweight title fight. these are like the early rounds where they're kind of dancing around each other, they're feeling each other out, they're maybe throwing a couple of jabs in. Nobody's hurt anyone yet because they're both slightly wary of the big punches they might be able to land. And so I don't think there's all that much behind this objection from Oppy. I'm not convinced he cares about it all that much. And of course, the other thing is that you could just change the premise quite easily. You could say it would be surprising for anything that arose from any human impulse to apply to the world, right? It's just surprising that the source of it is humanity, whether it comes from the aesthetic impulse or not. But what I would say is, I actually think I think maths does arise from the aesthetic impulse. And if you read what the world's most famous mathematicians write, they're consistently talking about beauty and about the romance of maths. And George Hardy said, if you take away the beauty of maths, there's nothing left. There's no point in doing it. And Bertrand Russell, he says, mathematics, rightly viewed, possesses not only truth but supreme beauty. And we get this kind of stuff all the time. I think I've got another quote somewhere down here. Michael Polanyi says, mathematics cannot even be defined without acknowledging its most obvious feature, which is that it's interesting. Okay, so mathematicians, I think that it is coming out of the aesthetic impulse, and I don't think that necessarily saying that it comes out of the problem-solving impulse is different to that. And I'll give you an example. Think about a musician, right, composing a great piece of music. Now, what impulse does that come out of? Well, surely everyone's quite comfortable saying that comes out of the aesthetic impulse, right? Producing a symphony or something like that comes out of the aesthetic impulse. But actually, there's a lot of problem solving in writing a piece for an orchestra, right? And for much of human history, maths and music were taught together all the way through the medieval world. Maths and music were kind of two sides of the same coin. They were taught together in the medieval universities all over Europe. And some of the first discoveries of maths applying to the natural world turned out to be musical ones as well. Or what about a novelist? When they sit down to write a novel, well, what are they doing? That comes out of the aesthetic impulse. And yet at the same time, you talk to any novelist and they'll have written out a plan. Where's this person going to start off? Where they're going to end up? How am I going to get them there? There's problem solving in that, right? So I just don't think that saying that problem solving and the aesthetic impulse are two radically different things. I think they've got this massive overlap in our kind of creative instincts. I think that Bill Craig is on safe ground saying that maths comes from the aesthetic impulse, but and I don't think Oppy is really opposing it in a kind of a strong sense. I think he's just throwing something in. But if you're going to say that maths isn't from the aesthetic impulse, I think you'd come dangerously close to having to chuck a lot of other stuff out as well, like music composition or writing novels or writing poems, because they're all problem solving too, And when someone sits down and does a Sudoku, or they're doing some kind of puzzle like that, what's that? Is that problem solving, or is it the aesthetic impulse? And actually, I think it's both, isn't it? There's like this. We do it for entertainment, I don't like Sudoku, but other people do. So, what are your thoughts on that, Cameron?
We're only talking about whether or not math arises from the aesthetic impulse, right? That's all we're talking
Correct.
about so far. Yeah. So I like the connection you made between the aesthetic impulse and beauty, and the connection between, or not the aesthetic impulse and beauty, the aesthetic impulse and music, and how music and math are connected as well. And when you were talking about that, I was thinking about tempo, and how, when the different bars and everything, and how the music fits together, and how you can have like weird tempos, and you can have different, you could have like a 4/5 or 7/8 or just 4/4. You could have different measures and everything, and that seems all related to math as well. So that's what I was thinking about, and I don't have any settled beliefs on this, but I think that another thing you said that kind of stuck out to me was just that even if Craig is wrong about this, or mathematicians are wrong, or just if everybody's wrong about this, that still doesn't really do away with the argument. This is kind of a side point.
Yeah, I think that's right. And I can give one more interesting example from Frozen 2, right? I mean, I end up watching these films quite a lot these days. And in Frozen 2, near the start, the mum sings a lullaby to the kids, right? Mm-hmm. And then later on, spoiler alert, everybody, Elsa finds out who she is, and there's this dramatic scene with this amazing song that goes on. And right at the climax of that song, the crescendo where everything rises, the melody switches, and the melody becomes the same melody from the lullaby at the beginning of the film, right? I'm tempted to sing it, but I don't think I'm going to. But go back and watch it. Watch the lullaby and the chorus of the lullaby, when you're on YouTube after this, and then go and watch this crescendo. Now, what has to happen for that? They're two different songs. You've got to plan that. There's a lot of problem solving to how am I going to build up to this key moment in the film and then draw in a plot point from earlier. How am I going to do that? Well, that's a literary problem, and it's also a musical problem that's got to be solved, right? But yet it all arises from the aesthetic impulse. And I think that, I listened to an amazing podcast by Marcus de Sortoy, who is the professor for the public understanding of science in the UK, the history of mathematics. And he picks out 10 key mathematicians. And in every single episode, these mathematicians are saying they're doing it for beauty. They're doing it for the love of maths. And de Sortoy says, I don't even care whether my maths is useful.
We've had a super chat come in. I was wondering if you'd be okay taking a question at this point. Yeah, it's all related. Okay, so from Silgefredo.
Yeah.
He comments a lot, and I always mess his name up, so I really apologize. All right, well, thank you for sending in your super chat. He says, if math is its own little world, is it separate from us, or can the conclusion be false in that we make this little world for fun or decide the aesthetics?
Yeah, okay. He's a smart. He or she is smart, and they're ahead of the game because we are gonna cover that. I think we'll naturally cover that in the rest of the conversation.
Excellent. So,
shall we carry on? And then if this person isn't happy, they can get another one in for free.
Sure.
Is that okay? It's okay. All right.
All right. So let's play the next clip. How about that?
Yeah.
There's a big dispute to be had about whether the objectivity of mathematics requires objects. And you might think that you can not tread the path of the fictionalist, but also not be a Platonist, right? And it would require some argument, which we don't have time to go into to consider whether that's an option or not. So unless it comes up in the later discussion, I would prefer to put aside the dispute between Platonists, fictionalists, and all the other sort of accounts of the ontology of mathematics, because our question is more about the application of mathematical theories to the world, and that may not turn on any questions about whether there are mathematical objects.
Well, I agreed with that, Graham, because my point was that whether you are a Platonist and a realist, or you are an anti-realist, in either case, there's no causal connection of mathematical entities with the physical world. They can't influence the way physics operates.
Okay, so this hopefully will help on that previous question, because there's this massive debate in the philosophy of mathematics. Okay, that is maths its own world, kind of in its own right, or is it a world in our heads? Okay, it's a little bit like the kind of realist, anti-realist debate that philosophers are interested in, but it's very specifically about maths. So, for example, the number 4, right? Does the number 4 exist in its own right? If there were no human beings and there was no physical universe, does the number 4 exist, right? Or is the number 4 a kind of concept that exists only in our minds, and therefore it's fictional, and we just use it, but it's not real. Okay, so you have mathematical realists and you have mathematical anti-realists, and the people, the terms that were mentioned, one was Platonists and the other was fictionalists in that clip. A Platonist believes that maths and the world of maths really does exist, right? It has some kind of existence entirely of its own, independently of us, and we discover things about it, right? But it's out there somehow. And the fictionalist says, no, maths isn't out there. It doesn't have its own objective existence. It doesn't exist on its own. It's a concept in the human mind that we've made up and that we use, but it's not real. Okay, and this argument's an interesting one, because when I listen to someone who argues that maths is real and has its own independent existence, I'm usually persuaded by them, and I'm like, yeah, okay, that sounds pretty good. And then if I find someone
Uh-oh. Looks like he's frozen. Says it's reconnecting with him. Sorry about that, guys. That's kind of an unfortunate face to freeze on as well. All right, there he is.
Why don't you do a little... Oh.
You're back. You were talking about fictionalism.
I think it... Yeah. Can you just say something else? I'll check I can hear you in my headphone.
Check, test.
Yeah, okay, brilliant, thank you.
Yep.
When I listen to someone who says maths is its own world, I'm convinced by them. And then when I listen to someone who says, no, it's not, it's just in our heads, I'm fairly convinced by them as well. So I'm on the fence. But Oppy and Craig agree on this. This is a point that they agree on. I think they agree on a huge number of things. And they both agree that maths doesn't have its own objective existence out there somehow. And of course, they also both agree that it doesn't make any difference to this argument, one way or the other. So they threw in some philosophy of maths, but actually it's nothing to do with whether or not maths applying to the physical world needs an explanation and what that explanation might be. Because we've still got the reality that we can use maths to describe the world. And it doesn't matter whether maths is real or not for that connection to exist. Okay? Is that all right?
Yeah, I am wondering about that, though. I mean, does it would seem to be a better problem if we were Platonists?
Okay.
Seem to be a more surprising, because I mean, if we can make stuff up, and you know, if that happens to map onto reality, you know, that's fun. But I don't know.
Okay. Well, that will come up again later, I think, and probably if there is a Q&A, but we'll see how we get on.
Okay.
But
yeah, I'm sure I'm not the only one that thinks that either. All right, let's play the next clip.
Now we're not talking about some amazing fit between the mathematics and the true structure of the world. We're talking about our ability to make models that will give you the right results across some domain to within some specified tolerance, some limits of accuracy. So when Gally points his telescope to the sky, Leverrier's calculation's accurate to within 1 second of arc, but when you calculate the precession of the perihelion of Mercury using Newtonian theory, it's just wrong. It's out by so much.
Mm-hmm. Yeah, I guess I just don't see the problem there. I mean, the equations were sufficiently precise to yield a real world result, the discovery of the planet Uranus that is out there. It is a real world result that was possible because these mathematical equations were accurate to a sufficient degree to be able to predict such a phenomenon.
Okay, so this is where I think actually now it gets interesting. This is like a big right hook from Oppy. I think it's a really good point, and it's got quite a lot of force. So I'm going to try and explain it. Craig is saying, look, there's this amazing power of maths to describe the world, and a lot of his argument is based on that relationship. And then Oppy's saying, well, yeah, but hang on a second, it doesn't actually describe the world. So I'll give you an example. Newton's second law, which is one of the laws in the paper of Wigner, is F equals ma, right? F equals ma. And this law is really powerful, and people get taught it in every high school physics course all over the world. And it's incredibly accurate, right? It's incredibly accurate. But it's not perfect. And the reason it's not perfect is that in this system here, this is acceleration, right? And so if you had a big enough force, you would be able to accelerate something to any speed at all. In fact, if you wanted to, you could accelerate it to faster than the speed of light, right? Now, that's a problem because what we now know is that nothing can travel faster than the speed of light. But F equals ma would allow it to happen. And so actually what we have to do is we have to change m. We have to change the law, and we have to include this new version of m, where instead of putting it in like this, it equals a different expression. I'm not going to explain what the expression is, but you can see that instead of m, I've now got to write a much more complicated expression for it. I don't know how well you can see that. I'm doing a darker pen.
Yeah, it's a little bit difficult. There you go.
Okay, so m is suddenly becoming a way more complicated term thanks to Einstein, right? And actually, if you just left it at F equals ma, you're going to start getting wrong answers. You have to start changing it to this, and then later on, it turned out that even if you change it to this, you're going to find that there are some answers missing, right? So Oppy now is saying, yeah, but hang on a second. A lot of the mathematical theories that we've come up with, they're not exact. They don't describe the real world exactly. What they do is they give it an approximate description of the real world. And I think this is a really forceful point, because first, I mean, it's true, right? First, it is definitely true that a lot of our best mathematical applications in physics do not give 100% accuracy. When Newton first formulated his law of gravitation, it was out by about 4%. Over time, the laws got better and better and better and better. When we got better at using them, we got better observations. But they're not exact. And the example that Oppy gave in the debate is it got Mercury wrong, right? It said that Mercury was in a different place, and you couldn't solve the orbit of Mercury using Newtonian mechanics. It's not correct. And if you do want to know where Mercury is, you've got to use this new method called general relativity, because the Newtonian mechanics is wrong. And I think the reason this is so successful as a kind of a point to put into the debate is I think it sort of busts a bit of the magic, the sense of magic, right? Wigner's called it a miracle. And what you might be thinking is, oh, right, maths describes the world exactly. That is pretty incredible. But now I've just been told that it doesn't describe it exactly, and that actually it is wrong. It's just not wrong by very much, but it's wrong. And the fact that we've got these physical theories described by maths that are wrong seems to just take all the wind out of the sails, right? It just seems to make it a much less impressive argument. And there's a couple of things worth saying about that. The first one is nobody claimed an exact fit. Wigner didn't claim an exact fit. He says, I think on the very first page, they often permit an unexpectedly close and accurate description. And it's the same with Bill Craig's version. He's very clear in his paper. He says we're only talking about an approximate fit between maths and physics. We're not talking about an exact fit. Okay. And I think for some people, that actually is going to be enough now for them to just say, well, I'm not interested anymore. I was interested when the fit was exact. But now that I know it's only approximate, even if it's to the 7th decimal place or the 8th decimal place, it just doesn't seem that impressive anymore, and there doesn't seem anything miraculous about it anymore, and it doesn't need to be, explained. And so I think Oppy kind of comes in with this massive right hook, and you're thinking, so what's Craig going to say? And he just says, I'm not bothered by that. Doesn't bother me at all, because I still think that you need an explanation for it, because it's close. It's very close to being true. Okay, and when I watched that, I kind of thought, that doesn't that doesn't win me over. And if we're going to stick with our heavyweight analogy, to me, it started to feel a little bit like the rumble in the jungle, arguably the fight of all time. Some people may know about it and some not, but that's the one where George Foreman has Muhammad Ali on the ropes, and he's just bashing him and bashing him and bashing him and bashing him. And the trainers, Ali's trainers, are shouting, "Get off the ropes! Get off the ropes!" to Ali. You know, they can't understand why he's not fighting back. And I think that it felt a little bit like that to me, that Oppy had come in with this brilliant point where, you know, it kind of sucks the energy out of the argument. And then Craig said, well, it doesn't bother me. It still needs an explanation. But here's an analogy that might help to see what Craig is getting at and why he felt so comfortable to just say, I'm not bothered by it. So I want you to imagine that in the morning, my littler girl, my 4-year-old, she comes down before me and she's kind of playing around in the house. And then I come down to give her breakfast and she's been drawing on my whiteboard. And what I find is that she has drawn a map of Manhattan, okay? And it's to scale. And she's drawn it like perfectly. And she's never been to Manhattan, and she's 4 years old, and there seems to be absolutely no way that she could possibly have done this. And she's even written the street names on, okay? And then my wife comes down, and I say, look at this. How on earth has this happened? I need some sort of explanation for this. And my wife looks at the map, and she goes, no. One of the streets is wrong. She's given the wrong name. She's got 2 of the streets the wrong way round. She's given them the wrong names. It doesn't need explaining anymore. But clearly that's nonsense. It does still need explaining. It's not enough to say it's not an exact fit, right? Something very strange has happened. We've been playing around with maths, and we've come up with, just by nature of fun, we've come up with something that almost exactly describes the physical world. And to just say, oh, well, it's not an exact fit, so I don't need to explain it, might be very much like saying, oh, yes, you got 2 streets the wrong way round on the map, so don't need to explain that when it still is. And I think that's why Craig is content to say, doesn't bother me. The fact that it's close already means it needs an explanation. And all I'm arguing is that it needs an explanation. Okay, so.
Yeah, I'm willing to go with that.
Do you want to say anything on that?
No, I'm willing to go with that.
Okay. Right,
should we play the next clip? Yep.
Let's do it.
All right, let's do it. Here we go.
Consider what Michael Friedman says in his book on space and time about the relationship between general relativity and Newtonian theory. It turns out that we can write both these theories in the language that was originally, the mathematical language that was originally invented in order to make it possible to represent general relativity. But you can rewrite Newtonian mechanics in that language as well. And when you compare the 2 theories, the difference between the theories is that Newtonian mechanics postulates some extra structure. It's not that it postulates less, it postulates more, right? Now, how can it be that that's a... How are we going to think about that as an approximation to the truth, right? When what it's done is it's postulated extra stuff that meant that it went wrong.
I think it would depend on whether or not that extra structure needs to be excised to get a more accurate description of the physical phenomena and to predict future results of experiments. As you may know, I myself think that the general relativity is wanting in structures, space-time structures, that they deleted some important things like hypersurfaces of absolute simultaneity that tend to be restored in, I think, astrophysical cosmology. But be that as it may, whether the structures are additional or deleted, it would be a matter of the degree to which the mathematical laws give us an accurate description of the phenomena and enable us to predict future phenomena.
I know you have a lot of interesting things to say about this one. We've talked about this before, so I'm looking forward to what you have to say.
Yeah, I've been playing around with it. Again, I think Oppy just shows his brilliance here, and this is like now a combination of body shots and uppercuts, and so I'm going to try and explain what it is that Oppy has said here, and then also why it is that it's so clearly caught Dr. Craig off guard. When the question comes in, there's like a 10-second pause, and you can see he's thinking, "Wow," And so what Oppy has said here is, now let me just show you something. There are two sets of mechanics that we can use to describe the world. I mean, there are plenty more as well, but we'll just talk about these. So there's Newtonian mechanics, and then there's also general relativity. So I'm going to abbreviate that to just N and GR now, right? And Newtonian mechanics is old, right? It came from in the 1600s. It's the F equals ma stuff that I talked about before. And general relativity is newer. It's about 100 years old. And that came from Einstein. So they came from kind of two giants, Newton and Einstein. Now, you'll remember that previously Oppy said, well, it's all very well saying this amazing stuff about maths, but Newtonian mechanics is wrong. He said it's wrong. It's a false theory. And sometimes what people do is they say, well, no, it's not false. It's not a false theory. What it is that general relativity is a more complicated or more complete theory of motion. But what you'll find is that if you take it kind of in the simple case, if you take a very simple situation, it collapses down, right? It collapses down into Newtonian mechanics, right? So in other words, they say, yes, general relativity is a better theory, but that's not because Newtonian mechanics is wrong. Newtonian mechanics is not false. What Newtonian mechanics is a kind of simplified version of general relativity. That if you take general relativity and you're only interested in treating everyday things like buses or tennis balls, then you'll find that general relativity basically just turns into Newtonian mechanics. And this is a defense that some people have used. They've said, this is just Newtonian mechanics with more detail. Or if you prefer, what they would say is that really what it is that Newtonian mechanics is the stripped down, simplified, everyday world version that pulls out of general relativity when you try and when you're just talking about normal things that aren't moving super fast near the speed of light, or they aren't near a black hole or anything like that. Okay, and Oppy now steps into that and he says, right, I'm going to give you a different way of thinking about it, because he says there's a problem with that idea. And what he says to Dr. Craig is, hang on a second, if you take Newtonian mechanics and you write it down in the language of general relativity, then Newtonian mechanics doesn't turn out to be the more simple version. This actually now suddenly looks more complicated than GR. And so his challenge to Dr. Craig is to say, all right, you tell me which one's more complicated then. If your line was going to be that Newtonian mechanics is just a simple version of GR, then why is it that when I write Newtonian mechanics in the language of GR, it gets more complicated and it looks like GR is a simplified version of Newtonian mechanics? So you're kind of caught in this loop where both of them look like they're more complicated than the other one. And that makes it really messy. That makes the whole thing really messy. And it basically removes, or Oppy is removing the option of saying these earlier mathematical theories weren't just simpler, stripped down versions of reality. They were actually, they're just totally wrong. And what's more, it might be that the other one's totally wrong too. So he's doing quite a lot of damage with mentioning this, and I think you, Cameron, wanted me to tell you very briefly what the difference is between Newtonian mechanics and general relativity, and it is quite simple to explain. In Newtonian mechanics, everything happens on this fixed background of empty space, where something that's a meter long is always a meter long, and something that is an hour long is always an hour long. So time is just well behaved, and space is well behaved, and they don't play any part in the physics. It doesn't matter what you're doing. An hour is an hour, and a meter is a meter. But general relativity says, no, it's not like that at all. Time and space aren't the background that everything plays out on. They are actually part of the show as well. They're actors in the show. And space itself can bend and change shape. And time itself can speed up and slow down. So actually, an hour isn't always an hour, or a meter isn't always a meter. And suddenly everything's playing out on a bendy background. And the presence of mass in the universe changes the shape of the background. It can make things move in curves along this background and all this kind of stuff. So the simple version is Newtonian mechanics, everything playing out on a flat, uninvolved, well-behaved, consistent space-time background. And general relativity, it's all, the space-time is bending and changing and flipping around and all that kind of stuff, right? So I was thinking about this, and I think it threw Dr. Craig, and I don't think his answer was one that he would give if he had more time. He mentions hypersurfaces of simultaneity. Well, don't worry too much about that. That's to do with whether or not everybody agrees whether two events happen at the same time. And in general relativity, they don't. They disagree about it. Okay. So I've got an analogy that might help here. Okay. So let me just find. Right, so here's an analogy. Let's imagine that there's some sort of important event that happens in Germany, okay? There's an important event that happens in Germany, and we get that one of the German newspapers writes a report about it, okay? So we've got a German report about an event, and this report, because the event happened in Germany, and because it was considered more important, the reporter was allowed a bit more of a word count, right? So maybe they were allowed 1,500 words, okay? And they were allowed to go into a bit of detail. And there's also a report in an American newspaper of this same event, okay? You still with me?
Yep.
Yep. So,
yeah, I remember this analogy. We were thinking through it earlier.
Yeah, that's right.
Yep.
Yeah. I've kind of changed it slightly. So the American report on the same event, well, it happened in Germany, so perhaps they're not going to give this person as much byline. And so when they write it out, their account is only 1,000 words, okay? 1,000 words long. And it leaves out some of the detail from the German report. So it's kind of it's a report on the same ultimate reality, but it doesn't have as much detail as a German report. It's less complicated than the German report, so you can consider this report to be like a stripped down version of this one. Yeah, is that okay?
Mm-hmm.
But then we could say, well, hang on a second. What happens if I take this report and I translate it into German? So I take this American report and I translate it into German. Okay, that's probably probably can't see that. Now there's a problem.
Yeah, you need some new markers.
Well, I did buy some new markers, but I think it's probably my webcam.
Mm.
Can you see that translate into German?
Yeah, I mean, yeah.
Okay. Now,
it's the reflection of the screen is kind of causing a little bit, but it's okay.
Yeah, right. Now,
no big deal.
The problem it's the translation that causes the problem, right? Because when I want to translate into German, well, Some of the stuff doesn't have like a quick and easy and simple translation. In fact, maybe in the American report, there are some idioms that don't exist in German, right? So maybe at some point in the American report, it says something like, still, a bird in the hand, ... right? You know, the idiom, a bird in the hand is worth two in the bush. You heard that before?
Yes.
Yeah. So maybe the American report says a bird in the hand, ... And of course, they don't need to say the rest of it because they know, everyone knows what it means. But maybe in the German report, when you want to translate it into German, when you want to translate the American report into German, actually what you need to do is use a longer sentence or 2 or 3 sentences in the place of that first half of that idiom, because the idiom doesn't exist in German. And so to make the same point, you've suddenly got to start writing a lot more, right? And maybe also some of the things that are expressed rather simply when you're writing in an American newspaper, to express them in German would be more complicated, right? The sentence structure might be more complicated and so on. And you find that when you do it, when you translate this American report into German, it turns out to be 1,600 words. Okay? So actually, now I've got an interesting issue, because I say, well, if when I translate this one into German, I get 1,600 words and I get extra content and there has to be extra explanation, well, which one is the simplified version of which? I thought the whole point was this was a simpler version of that. But when you translate it into German, now it looks more complicated than the original one was. So is this now an approximation of that one? Right? And this is because what you're trying to do is take something and change the language it was written in. Newtonian mechanics is written in a different language to general relativity. So when you try and write it in the language of general relativity, that's not the language it was designed for, right? And so suddenly you've got to start adding extra terms to keep certain invariances in place and so on. But actually, that's all false, because if you want to know what Newtonian mechanics is telling you, you've got to look at it in the language it was written in, the language it was formulated in. And if you want to know what GR is telling you, you look at the language that GR was written in. Now, you can sometimes get more information by changing the language. So, for example, here's an introduction to a mathematics course at Oxford University. I think it might be the 3rd year or something like that. It says, Newtonian mechanics is an extremely accurate theory. It's valid over a vast range of scales, and it's applicable to many classes of dynamical problems. And then they say, so what mileage could you possibly get out of rewriting Newtonian mechanics in a different language, right? Well, there are a whole bunch of different languages you could write it out in. And when you do that, sometimes you get extra information, you learn extra things, so you get extra conservation rules and so on. But I think that the mistake that Oppy has made here is that he's saying, look, you want to call one thing the approximation of another, and then you change the languages you've written in, and suddenly your approximation language is gone. I think the mistake is that it's a red herring. I think it is actually a red herring, because the whole point that Craig is trying to make is that maths can be used to very accurately describe our world, right? That's the point that Craig is making. And so it's almost like Craig is saying, written language is a very good way of describing events. Right? Craig is arguing written language is a very good way of describing events. And then if someone came along and said, yes, but there's German and there's American in written language, and some people say that American is just a simplification, this American report is just a simplification of this German report, but when you translate it, you find out it isn't. Well, that does lead to a very interesting discussion, right? And people could have all sorts of arguments about it. But it doesn't undermine the key point. And the key point is that maths is very, very effective at describing the physical world. And that not only that, it's so effective that there are multiple different mathematical languages and multiple different mathematical theories that all describe our world to varying degrees of accuracy. So general relativity is more accurate, yes, than Newtonian mechanics. But they both do describe our world, and they both describe them well enough for any result that we're kind of interested in on a practical level. And then every now and then GR has the edge when you want to calculate, say, the orbit of Mercury or something like that. So, I mean, I think it was a really good point from Oppy, a really interesting point. But I think what it does is it takes your eyes off the prize. And the prize is maths good at explaining the world? You know, and the answer is yes, it's very good. In fact, it's so good that we've got Newtonian mechanics and general relativity, and they both explain the world. Where I think Oppy is successful is I think it is a successful, it's a really good argument against anybody wanting to argue that Newtonian mechanics is purely and only a simplification of GR. I think it does call that into question. But that doesn't call into the question the bigger picture. Now, does that follow or not?
Yeah, no, I like that, and I like the adjustments that you made to the analogy. I think that it works really well. So I don't have anything to add. Yeah, and people in the comments are even saying the same thing.
Okay, that's good. All right. Good, let's crack on then.
All right, next clip. Here we go.
An example, right? Imagine a cliff top and you're throwing a rock into the ocean, right? So you've got you set up your model, have sea level at 0, the height of the cliff's h. There's some angle that you project the rock. You get an equation of motion and you work out some time at which the rock intersects with the water. Now your equation is a parabola. And so there's another solution where it intersects the x, x equals 0, the y-axis, at some negative time, some earlier time. And when you look at that, you don't think, so maybe there was an anti-rock and it tunneled up through the cliff and then it was annihilated when the... Yeah. What you do is you say, that's not a physical solution.
Yes.
Right? And that's a kind of universal thing in physical, in kind of modeling, physical modeling of the universe, right? And so, I mean, I wondered about the bearing of that on some of the examples that that you've used previously, and some of the examples that Wigner gives in his paper. For example, right, there's Dirac's prediction of the positron, right? But Dirac also predicted magnetic monopoles, which we haven't yet found. What if we never do?
Well, both Wigner and Steiner discuss this fact. I mean, the failures, the mathematical failures outnumber the successes. There's no doubt about that when you think about it. The realm of mathematics is infinite. The physical world is finite. So, of course, most mathematical concepts or formulations will fail to apply. But I don't see the cases in which mathematics fails to apply does anything to explain the cases in which you do have this breathtaking accuracy and detail of mathematical descriptions of the universe. I think you can acknowledge the failure of many mathematical concepts to apply and of laws of nature that are false, but that just doesn't do anything to render it likely that on naturalism you would have this sort of mathematical precision characteristic of the physical phenomena.
Okay, this is another body blow, maybe like a liver shot this time, and I think this is another brilliant point from Oppy. He's saying, hang on a second, you're saying that mathematics has this brilliant ability to describe the world that demands explanation, but there are loads of times when it doesn't describe the world. We're not talking about approximate theories anymore, right? We've had that discussion. You know, it's only an approximate thing. He's not talking about that now. He's saying there are things that are nothing to do with the world at all, right? There are loads of things in maths. In fact, there might well be an infinite number of things in maths that don't have any correspondence whatsoever to the world, right? And I think that's it's a very successful point in making the whole thing look less miraculous, right? Because once you suddenly say, but the world of maths is infinite, well, of course, it feels like, well, of course it's going to describe the world, right? If maths can say anything, then some of the things in maths are going to match up with the real world. And loads of other things aren't going to, right? An infinite number of other things aren't going to. But I don't get why you're surprised to find that an infinite regime, some of it will map onto a finite regime. That almost seems like a principle of logic, right? That if you've got an infinite number of possibilities over here and a finite number here, some of those are they're just gonna match, right? So that's not a miracle at all. It's just obvious that is what's going to happen. And he gives some examples. He says, okay, you throw a rock off a cliff, and when you solve the problem, one of the equations that you use to do it, and don't worry, I'm not going to solve it or anything. This is one of the equations that you can use to solve it, and it's got a squared in it, right? It's got times squared in it. And the thing about a squared graph is that it has two solutions, right? Or it could be like that, it could be like that, depending on whether we've got positive or negative acceleration. It has two solutions to it. It has a solution here, and it has a solution here as well, right? And Oppy says, okay, well, when you throw a stone off a cliff, and you want to know how long it's going to be before it hits the water, and you find out that it's 3 seconds, that's not really what the maths tells you. Okay. In reality, what the maths tells you is that t could be 3 seconds, or it could be minus 3 seconds. That's what the maths equation, when you solve it, tells you. It says it could take 3 seconds to land, or it could take minus 3 seconds to land. And then what the physicist does is he says, oh, well, it obviously isn't going to take minus 3 seconds to land, because that's nonsensical. And therefore, I'm just going to ignore that result, and I'm only going to keep the one that makes some sort of sense, right? And Oppy says, but that's cheating. You can't just be selective. If you're arguing that maths does this amazing job of describing the real world, but what you're really doing is taking all the answers that maths gives and then ignoring the ones that don't suit you, you're cheating, right? But he probably gave the wrong example. And the reason for that is that the minus 3 seconds does tell you something. So here's my cliff, right? And I throw my stone off it like this, and it falls down like that, okay? And it takes 3 seconds to do it. The minus 3 seconds is not just a nonsensical, useless piece of information. The minus 3 seconds tells me this. It tells me if I was going to throw it from sea level, right? If I was going to throw the rock from sea level and get it to land there, where and when would I have to throw it from? And the answer is I'd have to throw it 3 seconds earlier in time to get it up to here, to get it to go down there. So my minus 3 seconds is not a useless piece of information at all. It's telling me something else about the world. It's saying, what if I didn't throw it from here? What if I want to know where it would have had to come from if it was going to follow the whole path, right? And I was speaking to, the other example that he gives is that Dirac, P-A-M, Dirac, Paul Adrian Maurice Dirac, discovered the positron in his equations, and he said, oh, I think it's going to be a real particle, and it turned out to be a real particle. But he also discovered this thing called a magnetic monopole in his equations, and we haven't found any of those. So surely you're going to say that the first one is some sort of miracle, that he predicted a particle that we did find. What are we going to do about the fact that he predicted a particle that we haven't found, right? Who's counting the failures? What if there's an infinite number of failures? Now, we've got to be careful here too. Dirac's equations only require there to be one monopole in the entire universe, right? So, we only need one. And a lot of people would put their money on saying, yeah, well, we are going to find it, right? There's been lots of times in history where the maths has predicted something and we've had to wait a long time to actually find it. The neutrino was predicted, it took a long time to find it. The Higgs boson was predicted, it took a long time to find it. And I just think we should be cautious with this. Bernard Riemann came up with the maths for general relativity, like in the mid-1800s. Einstein didn't use that maths or find out that it existed in the real world until 1920-ish, right? So actually, what if, let's say that someone was keeping a record of successes and failures, right? Let's say that someone was doing that. How do you know that the things on the failure list won't turn out at some point in the future to actually describe something that we just haven't come across yet, right? How on earth do you prove that something is a mathematical failure? You can't prove it because it might turn out to be real. And that has happened over and over and over again in physics. One professor that I was speaking to a couple of weeks ago who enjoys this sort of stuff, he was saying he thinks it might be possible that every idea ever invented by any mathematician in their mind might actually turn out to be a real description of something in the world. And he questioned whether it would even be possible for us to conceive of something in our mind that isn't instantiated in reality somewhere. Right? That was his take. Now, that's a bit extreme, and you probably won't find that many people taking that view. Where I think, again, Oppy is really successful is that at first it looks like he's made the whole thing look unspectacular. But here's an analogy again to help. Let's think about my daughter and the maps again. What if I say to my wife, she's drawn a map of Manhattan, and it's incredible, right? This needs an explanation. But later that day, we've been out in the house, we've been out in the garden. We find out that she's drawn, hundreds and hundreds of thousands of maps. She's been doing it in little notepads in her room. She's done loads, and most of them don't represent any real cities at all. Okay? Well, what Oppy is kind of saying then is, well, it now looks a lot less special that she drew a map of Manhattan on the board, because she's been drawing maps everywhere. She's been drawing them all over the place. And most of them don't correspond to any kind of city that we know about, right? And so it kind of reduces the force of the argument. But again, I think what it does is it takes the eyes off the prize. She's drawing maps. What on earth is a 4-year-old doing drawing maps, right? Carefully structured, well-designed, sensible maps. No one's taught her to do that. It was very strange that she's just been doing that, and she's been writing down street names, and she understands that streets end with street or whatever. And then one more, so it still requires explanation because she is doing something meaningful, right? She's doing something meaningful that has structure. She's not just randomly drawing lines. Everything she draws is a map, okay? So we got to be careful about this. And then also the last thing to say about this point is it's a bit lazy to say that the mathematical world is infinite when we're talking about its applicability to physics. Because when we're talking about applicability to physics, you can't just dream up any possibility. They come with constraints. So if you've decided to go 5 steps along a particular line, you now don't have an infinite number of options to pick from at the next stage. That narrows down what your options are. And so when we do maths along well-defined lines, and we're trying to describe, in other words, you couldn't just come up with any world you wanted in maths. If what you're thinking about is a kind of physical match, there are rules. There are rules where you've got to travel along a well-defined line to come up with a consistent world, right? But that's less important, that particular point.
So my question, my question is, what was Dr. Craig's response to Graham on this, to Dr. Oppy?
So he said, well, of course, the mathematical world is infinite, so most of it is going to fail. But I'm not interested in that. I want to know why does it match, right? Why does the physical world have mathematical structure? That's what he's saying. So he's saying, it's fine. It's absolutely fine that the mathematical world is infinite. There's no issue with that. But why does the physical world have consistent mathematical structure? Why is it consistent with this infinite realm, right? And so that's what I was trying to say with my daughter. At first, you kind of say, well, doesn't need any explanation anymore because she's been drawing maps. But the bigger question is, why has she been drawing maps? Okay, you start with the thing you're trying to explain, and you say, well, that still needs explanation. It still needs explanation that the physical world follows a mathematical structure. It could have been different, or we think maybe it could have been different. That will come on to the when you hit the philosophy later. But you could conceive of a world that doesn't have mathematical structure, right? Or actually, I think it's a stretch genuinely to try and conceive of a world that doesn't have mathematical structure. But I'll give you an example. Let's say that we lived in a world where when you put one object next to another object, there was some sort of event that occurred, some sort of force or rule or something like that, that meant that that another one appeared. Now, how would we do arithmetic in that world? We would write down 1 + 1 is 3. Because every time we put two things next to each other, something generated a third one, right? So we start now. That's still a mathematical world, but what if it was inconsistent? What if sometimes I put two things next to each other and a third one appeared? And what if sometimes I put two things next to each other and 4 things appeared? Or what if the number of things that appeared depended on how close they were to each other? So I put one here and I put them far apart. Okay, I put them far apart and I get a third one, like this. But if I put them close together, I get 2 more things. How would you do maths in that world? Sometimes 1 + 1 is 3. Sometimes 1 + 1 is 4, right? And what if it was random? What if there was no relationship between the distance? What if when you put things down, other things came into existence, but there was no observable pattern? You couldn't even do maths in that world, right? So can we kind of conceive of worlds where there isn't this maths? Maybe we can. I think it's a little bit of a stretch. But the question is still, the world has got mathematical structure. The mathematical world is infinite, but the physical world has got mathematical structure. Why has it got that structure? But I think this is still, I think Oppy's point is still forceful. I think it's a good point, and it's one that merits more discussion. Maybe the answer is that all of the failures, all the things we chalk up as failures, aren't failures at all. Maybe they are actually descriptions of physical reality in areas that we don't understand yet.
There's some way that they're still applicable. I mean, you gave the example of like if you were throwing it from sea level, maybe,
Yeah, that's right.
So there's ways.
Maybe they all turn out to be.
All right, let's play the last clip that we have, and this is where we're going to start to get into the philosophy. And the last part of the discussion was Graham started to give some of his own views on how naturalism might explain the applicability of math in the world. And I'm going to give a little analogy to explain where he's coming from, and hopefully it'll be helpful. So here we go.
There are versions of naturalism that can explain this in a very straightforward way. Right. And so one of the versions of naturalism that can do this is one that I've been playing around with for about a decade now. And so let me give you the kind of tenets of the theory that you need in order to explain the effectiveness. Right. You may, when I get to the end of it, you may think it's, disappointing that it turns out that this is the way the explanation goes, but it's definitely an explanation. So start with this, a theory of modality. So every possible world shares some history, initial history with the actual world, diverges from it only because chances play out differently. Right, so that's all the possibilities there are. The only possibilities that you need really are for chance. And we're talking metaphysics here. We're not talking doxastic possibilities or epistemic possibilities. We're talking metaphysical possibilities. So that's all the possibilities that there are. The laws are necessary. The boundary conditions are necessary. This is true. It doesn't matter whether we're thinking about one universe or many universe model. So we're supposing that where contingency comes in is in the outplaying of chances. That's the only place that contingency comes in. We suppose also, and this is the only kind of new assumption that we're going to make to go along with the kind of metaphysical picture that we've already outlined, which is going to be a naturalistic picture, is that the laws and the boundary conditions are amenable to mathematical formulation. On that assumption, and given the other assumptions, it just turns out that it's necessary that that's the case. It couldn't possibly have failed not to be so. Now, add in a couple of other things that I don't really need, but that are also part of this picture that I developed when I was thinking about the origins of the universe, had nothing to do with the applicability of mathematics. There's no explaining why something's necessary. Once you get to the postulation of necessities, you've reached the end of the explaining that you can do. And last of all, if you've got a non-modal claim, P, and you believe that, or you accept that necessarily P, then it's being necessary that P explains why P. Okay, so now, given that, we have an explanation for the effectiveness of mathematics, which is that it had to be. Because it had to be, it's so. Right? And it just falls out of the picture. Now, that's a naturalistic story that has an explanation. You might not like the explanation, but at least for me, it comes for free from things that I've said elsewhere.
Yeah.
Right?
Well, I hope that our listeners have understood your alternative, because honestly, Graham, I think it takes more faith to believe that than it does to believe in God.
It's a fun comment from Dr. Craig there. So let me see what I can do to explain what I think was going on with Graham's view of what he calls modality, and modality is just philosopher talk for possibility and necessity. So I think we can actually kind of avoid that and just talk about, let me give an analogy. I've got a slide up here. This is a car factory. So suppose that there is one car factory in the whole world and they produce Ford cars, okay? And so Dr. Craig is, he comes out and he goes, well, why does this factory only produce Ford cars? Like, why aren't they producing other types of cars, Volkswagen, Audi, something? Why are they producing Ford? And Oppy, Graham, comes in and he goes, well, look, this is what's happening, is the car manufacturer is actually at the beginning of the universe, okay? And there's actually no other way that the beginning of the universe could have been. So there's no other type of car manufacturer that could have been. It's just necessary. It sort of had to be that way. The car manufacturer is at the singularity. That's a term that he used. It's at like the beginning of the universe, or whatever the start of the universe was. The car manufacturer is there. So any questions of like, why is there a Ford car? Why does this factory produce Fords? There's no explanation other than it's just necessary. It has to be there. So I think that is a very simple way of explaining sort of what's happening with Graham's with Graham's view, is that on naturalism, to bring it back to the point about math and everything, is that on naturalism, or on Craig's view or not Craig's, but on Graham's view of naturalism, is at the beginning of the universe, if we can describe the beginning of the universe or our universe in mathematical terms, then it sort of has to be that way, because every different way that things could have been, every weird different possibility that could have happened, if there was a different universe to ours, for example, maybe there's a universe where Dave and I aren't having this conversation. That seems like a possible universe. But if all of think of like a tree branching out. So if all of the different branches ultimately go back to like this one place, this one stem, there's no explaining. There's no need to go beyond the tree itself in order to explain all the branches on the tree. So what's is that making sense to you, Dave? Are you tracking along with this analogy?
Yeah, I mean, I think again, it's amazing how much they agree. Craig and Oppy in that they're envisaging something pretty similar to each other, which is that you keep going back and you keep going back and you keep going back, and you ask the question. The question we're asking is why does the physical world have this mathematical structure? And essentially, Oppy's answer is
it has
part
to.
Of the necessary. Yeah, that's right.
It has to. It has to have this structure.
Correct. Yeah, it has to have that structure because what he calls a singularity at the beginning, and this is only one version of his naturalism, right? So he's not opposed to maybe there being infinite regress, that it just goes back forever, but if it does have this kind of start, which he calls a singularity, then within the singularity are the properties that cause the universe that we now have. And there were all these other possible universes that the singularity could have caused, but they didn't happen because it's probabilistic and we're just on the route that has played out by chance. So you track it all the way back and you say, why is it like that? And you say it just has to be, right? And then Craig's version, go on.
I was just going to add that kind of what's doing some work here is that Graham wants to say that the fact that the universe can be explained and the applicability of math, and that math, our concepts of stuff that we made up due to aesthetic impulse or whatever else, the stuff that we made up in our minds about math, the fact that it applies to the universe, or that they can apply it all, that is explained. It's a necessary fact. It couldn't have been otherwise. It has to be that way. And then on Graham's view, you're done. Once you've got that, once you've got the necessary part of it, it's like once you arrive at a necessary fact, then you're done explaining. You don't have to do any other work. And I think what Craig's gripe is, he seems to think that that's kind of cheating, seems to think that that's question begging to say that it's necessary. I have some, as I've thought about this further, I have some of my own worries with Graham's view that I can kind of get into a little bit. But it seemed like you had something else that you wanted to say.
Yeah, I think that it's almost like they're kind of arguing towards a draw, because Craig is saying, or what Oppy sort of later forces Craig into saying, or persuades Craig to say, is, why would God make? The question is, why would God make a world that had this mathematical applicability in it? Right? Why would God do that? And could God not do that? And Craig says, yes, God could not do it. Like God had the option of not doing it, but he didn't take that option. The option that he took was to create a world where it does match. And Oppy then says, well, that's just brute contingency, right? Your explanation is no more of an explanation than mine. Oppy is saying my explanation is that it's necessary, just has to be like that. And your explanation is, well, God just did do it like that. But we don't know why God did it like that or anything. So you're offering me a brute contingency, and I'm saying, I've got a brute necessity. And actually, how are you going to decide between those? Oppy says, maybe it's a draw, but Oppy then says, I think the advantage lies with me because I'm not also postulating a God, and you are also postulating a God. So if you're going to go with simplicity, my brute necessity is better, it's more simple than your brute contingency, right? Because you've got to postulate extra stuff, deity and all this kind of thing. But actually, I think we can do better than that. Have you got the slide?
Yeah, let me pull it back up.
Slide. Okay. So this is a book that's well worth having a look at for you guys in the States. It's called The Genesis of Science by James Hannam. In the UK, it's called God's Philosophers. And he's talking about science through the medieval period, the Middle Ages, and pointing out that it wasn't the Dark Ages at all. And here's a quote from it. Everyone agreed that theology was by far the most important and highly skilled profession of all. Only the most rigorously trained individuals could practice it. It took 7 years to qualify as a theologian, and that was after having spent at least 4 years working on a first degree. And amusingly, it then says, if a philosopher did want to tackle matters of faith, then he was perfectly entitled to join the theology faculty and train up, train as a theologian. And I think that sometimes we've lost this view of theology, that as Christians maybe, we're like, okay, if you really want to get into the proper depth, you do philosophy, right? And philosophy is the deepest of them all. But I think that for a Christian, theology is the deepest of all. It's the most real. It's the most profound. It's where you're going to get your kind of ultimate answers, even more than in sort of philosophy. May have just turned off half of your audience there, but just bear with me, because I think we can say better, more than a brute contingency, right? I think we can say that here's a conceivable reason that God made a mathematical world. So I've got a quote from Johannes Kepler, who is an amazing physicist who discovered that the planets orbited in ellipses around the sun. And we still, I teach his laws to my students. And here's a quote from him, which I think is really genuinely profound. And it can help us towards an explanation, or a possible explanation, of why God would make a world where mathematics is applicable to the physical sciences. So it says here, "For the theatre of the world is so ordered that there exist in it suitable signs by which human minds, likenesses of God, are not only invited to study the divine works, from which they may evaluate the founders of goodness, but are also assisted in inquiring more deeply." Now, that's a very rich phrase. So I want to go through it line by line and say, look, I think there's something we can learn from each line in there, right? So he starts off by saying the theatre of the world. So his attitude towards the world is there should be something entertaining about it. There should be something spectacular about it. It should be something to command our interest. It's something that we watch. It's something that we kind of enjoy. There is a show. There's a divine show going on in the world. It's so ordered. Now, not only is it like a theatre, but the show that's on is ordered and structured. It's consistent. It behaves in a way that makes it possible to try and understand it. That there exist in it suitable signs. So God has put into the world signs that this world came from a mind. It came from a person. It came from a being. It came from somewhere personal. Suitable signs by which human minds. So we've got this mind. We've got this processing ability in our head, which is somehow able to interact with the physical world. Likenesses of God. Oh, okay, so our minds are able to interact with the world because our minds are the likenesses of God's mind. When God made us, he made our minds like his mind. And so we are then, it says, I'm not only invited to study, this is invitational. God is saying, I have made a world that I'm inviting you to study. There will be a match between your mind and the world I put you down in. The divine works, that when you study it, you're going to find things that make you think about the divine. As you study it, you're going to learn about divine works, from which they may evaluate. So evaluate means measure the values of things, right? To do physics. They may evaluate. So you've got to draw conclusions from it. He wants us to think about the world, the founder's goodness. And as we think about the world, we're going to go, wow, this must have been put together by somebody who actually cares about me, because he's put a mind into me that means that I can look at the world and understand it, and he's invited me to study it. Who would do that? That would be someone good. That would be someone who has put some value on me, who's interested in me, but are also assisted. God is actually going to be helping us to do this into inquiring more deeply. Right? So that actually the deeper we go, the deeper we study the world, the more we should find this, right? The more study of the world that we do, the more signs we should find, the more our mind should resonate with it, the more we should feel that maybe there's something special going on, okay? And so God has created a world that is resonant with us. And so is it possible to switch back to the whiteboard, Cameron? I want to try and show it as a diagram. So we've got here, in this circle here, don't worry, I'm not going to do any more maths. This is the world, okay, that we have been put into. And then here, this is the human mind that God has put into us, Okay, and then lastly, we'll put here in this circle, we'll put inside here, we'll put maths. Oh, it's not showing up great. Let me just see if I can find a better pen. There we go. Let's put maths in this circle here. Now, what Kepler is saying is that God has designed the world to be mathematical. So there's a link here, right? God's designed the world to be mathematical. It has mathematical structure. But he's also designed the human mind to be able to do maths. And then not only that, what he has done is because of that, because we can do maths, we can understand the world that we live in, right? We're connected to the world. We can understand, we can study the world. So there's this resonance between the mind, the properties of maths, and the physical world that we live in, right? Now, why would God do that? Well, I think God ties all of this together because it gives us joy to study maths. It gives us joy to study the world. And you say, well, what would happen if one of these things was missing, right? So let's say that God did not create the human mind so that it was able to do maths, right? Well, what would it be? What would that be like? Well, we'd want to study the world, right? And the world would have a mathematical structure, but we wouldn't be able to do any maths, so we would forever fail to understand the world. Does that make sense? The world has a mathematical structure. Okay, so God makes it so that our minds can do maths. All right. Well, what about a different possibility? Let's say that this branch is missing. Okay, so the human mind can do maths. It can really enjoy itself doing maths, and the human mind can study the world, but the world doesn't have a mathematical structure, right? Well, then the people who did maths would be sitting somewhere and they'd be doing all this stuff and it would never have any purpose, never have any bearing. And so an entire group of people would never bother, or they wouldn't be interested. We'd be doing this maths, it would never relate to anything. Well, it wouldn't draw us into anything higher. It wouldn't make us think, oh, hang on a second, what this is really resonating with the world, right? So by putting that link in there, we have a Nobel Prize winning physicist, Eugene Wigner, writing a paper that has the word miracle in it 12 times and wanting to know what's going on, right? Or what if this was missing here, right? So here, the human mind can do maths, and the world has a mathematical structure in it, but, we're not interested in the world. Well, then there'd be no value in the world having any mathematical structure. We would miss out again on kind of joy, the joy of realizing, wow, God has put us into a world that's got this stuff in that we can do, right? So I would say that the explanation is the goodness of God and the kindness and the generosity of God, who says, I'm going to make you with this mind, with this highly capable mind that has this mathematical ability, and then I'm going to put you in a mathematical world where you can use it, right? So, it would be really cruel if I said to my daughters, I'm going to buy you some brand new swimsuits, and I'm going to buy you some pool toys, and I'm going to buy you a bodyboard, but I'm never going to let you near a swimming pool, right? That would just be mean, okay? Or if I said, yeah, sure, I'm going to take you to a swimming pool, but I'm not going to give you any stuff, right? But this is now God saying, I'm going to put you in a world that's going to fascinate you, and I'm going to give you the tools to study it, right? And not only that, I think it goes even deeper, because I think it can give an explanation for why maths only approximately describes the world, which of course was one of Oppy's criticisms. If maths exactly described the world, then maybe 500 years ago, someone would have figured it out. They would have got the theory of everything, right? Maths is complete. Nobody else has to do any more maths. Nobody else has to do any more physics. It's like a dead enterprise, okay? Now, you might think, oh, but that's the end goal. The end goal is to get a theory of everything, right? But actually, no, we love this stuff, us mathematicians. Imagine this. Imagine that 500 years ago, someone wrote the perfect song, right? And because of that, everyone decided there's no point in writing any more songs. because someone's written the perfect song. Music has been completed, right? All the joy of music just disappears out of the world. Or imagine 500 years ago, someone painted the perfect picture, right? But actually, this makes sense. It would make sense if it's about enjoyment and blessing and the goodness of God, then he would make sure that in every age, someone could discover something, right? In every age, just like in every age, someone can compose music. In every age, someone can, draw art, right? Well, now we're saying God has set up a world so intricately that we can do this and enjoy this and never get to the end of it. We'll keep discovering new things. We'll keep being amazed at the fact that we found something in the world of maths and then we've applied it to the physical world, right? So God has given it again, I think, so if you say, what about the goodness of God as a reason? I think that is feasible, right? And I think that, this is when we do theology, that yes, our world is broken. And yes, there are things in it that aren't right. And yes, we're looking forward to a new creation. But there are lots of things in this world that are good, right? Think about food. God could have made it so that we were creatures that needed to eat, right? But food was boring. But, you Americans, you know how to do food because, you make it tasty, but you also do a double-sized portion like every single time. And so eating is pleasurable, isn't it? Right? Eating a nice meal is a pleasurable experience. It's not functional. And the same, doing maths is pleasurable. It's not functional. So I would say, I think we can go a step further than just saying brute contingency. I think we can say, actually, God has told us what he's like. The Bible has, on average, 3 questions per chapter. Right? The Bible's a book full of questions. And Jesus asked loads of questions. And right at the beginning of the Bible, Adam and Eve go missing. And God says, where are you? To Adam and Eve. Why did God say, where are you? He knew where they were. He's encouraging them to ask the same question. To think, hang on a second, why are we hiding from God? And God wants us questioning. And I think by creating a world like this, we get enjoyment and we also question. And we chase this stuff down. So I would say it's not a brute contingency. What I would say is that actually a mathematical world is totally consistent with the God revealed in Scripture, and we shouldn't be remotely surprised at it at all. And so we can bump it up another level and say, I think it becomes likely, right? I just wouldn't want to have to quantify that.
That's super good. That was great. So I want to add one more thing, and then we'll close this video out. So on Graham, what Graham was doing was he was giving a metaphysical account of how this all works, and he was explicit. Like if you go back and listen to what he was saying, is that he was in metaphysical. All that means is that he's talking about fundamental reality. He's not talking about like our beliefs or what we think might be likely true, given like what we are currently thinking about, or what we find likely or unlikely. He's talking about metaphysical reality, and so if reality can only be one way, is what he's saying. Like once you get back far enough, it can only be one way, and then possibilities play out from that one point. If reality can only be that one way, then the fact that it's necessary explains why there's this mathematical structure. And so he has this kind of get out of jail free card with his theory of modality. But here's what I want to say in response to that is that suppose that we were looking up in the sky one night, and we saw that there was we saw that Kepler, actually this might be interesting. We saw that the quote from Kepler, let me see if I can pull it up here. We saw that this was written out in the stars. Okay, it was formed in such a way that when we viewed from Earth, we saw that there was that this little passage was written out using stars in the sky. Okay, now on Graham's view, there would be no real deeper explanation because it would just be necessary that the stars formed this, amazing passage from Kepler. But we would still want to be like, there's some explanation. There's got to be some reason. There's a better explanation. It's more likely on some other hypothesis. And so what's happening is that while Graham can have this like metaphysical view of reality, there's still this question of what just seems most likely to us. And so to use a technical term, he's talking about what's sort of metaphysically necessary, and the real relevant question that remains is about what's epistemologically most likely. And so even if it's necessary, the world has to be this one way, its reality has to be this way. Think back to the example. If we found a message written out in the stars, then even if it was sort of necessary that the stars had to be in those specific positions, it's still just super unlikely that they would be there without someone putting them there, without, God involved or someone else involved. And so that's something that he would, I think, still have to deal with. Feel free to share your thoughts on that, but we do need to close this video out.
Yeah. Well, I think that basically what it does is it draws these two arguments together. It draws this argument together with the fine-tuning argument, and it puts them almost on the same footing, and then you have to analyze them the same way. I think that Oppy, everything that Oppy believes, everything that he believes, would change entirely if Jesus Christ rose from the dead. I just think that's the game changer, right? Like, you take Oppy's entire philosophy, and if Jesus Christ really did raise from the dead, then I would say, well, that changes the game enough to say, okay, I'm not only going to be a theist now, I'm going to be a Christian. Because what he's trying to do is get as much bang for the buck as possible. That's what he always says. He says, I want as much explanation as possible from putting as little commitment in as possible, right? Which may or may not be the right way to do it. I mean, why pick the simplest thing? Why don't you pick the most glorious thing, for example? But if the data includes Jesus telling everyone that he's going to come back to life in 3 days, and that's going to be the proof that he's the God that made this universe, and then he really did come back to life after 3 days, then surely Oppy would have to say, okay, I now switch, right? So it kind of moves the argument elsewhere. I'm not a Christian because maths can describe physics. That's not why I'm a Christian. I'm a Christian because I believe Jesus rose from the dead, right? I have the conviction of the Holy Spirit that Jesus rose from the dead. But then when I do this maths, or physics, I love it. I mean, I love physics and I see maths as a tool. But that's not the reason that I'm a Christian. And it's not the reason that Bill Craig is a Christian either. He's just offering it as he's saying, look, this is a situation that is easier to describe if I'm right.
All right, well, let's leave it there. We've talked a lot, and this is a very long video already. So why don't we leave it there, and then I'm going to offer it to you if you're watching this and you have any additional thoughts or clarifications or questions that you have about the debate between Dr. Craig and Dr. Oppy, then leave it in the comments. Let me know what you think about this breakdown. Let me know if you'd like us to do more of these types of breakdowns of debates. And I don't know who else I can get that is as amazing as Dave at breaking things down, but we will see what we can do. But in any case, I really appreciate you tuning in today to Capturing Christianity. My name is Cameron Bertuzzi. I never mentioned that, but that's who I am. And Dave has been on the channel a bunch. He's probably going to be featured more. So I appreciate you watching, and we will see you guys later.